Hello everybody and welcome to today's presentation. What's the deal with data and microservices applications? Brought to you by NuoDB. Before we get started, I'd like to take care of a couple housekeeping items. First off, I'd like to make sure all of you can hear me okay? So if you would, just send me a quick message in the chat window to let me know. Great. If you have any questions for our presenters today, please post those into the questions panel so we can get to them after the presentation. If you experience any technical difficulties today, like the audio dropping out or the screen sharing not displaying properly, please post a message in the chat panel to me, the host, and I will work with you to resolve those issues. Lastly, on the housekeeping list, we are recording today's presentation and will be making it available shortly after today's event concludes. Now that we're through the housekeeping items, I'd like to introduce our presenters. As Senior Product Manager at NuoDB, Joe Leslie helps drive NuoDB product releases and roadmap to ensure NuoDB's database leadership position, delivering elastic SQL database scale-out and continuous availability for hybrid cloud applications. Joe has over 20 years of experience delivering database products and management tools in the transactional and analytical database marketplace. Marius works as Chief Architect at Red Hat, leading the efforts around data streaming and Red Hat middleware, enabling the development and operation of data streaming solutions for Red Hat portfolio, targeting OpenShift. Marius has a long-standing interest in enterprise application integration, event-driven architecture, and data strategies. And before joining Red Hat, he was leading Spring Cloud Stream as part of the Spring team at Pivotal, as well as contributing to various projects in the Spring portfolio, such as Spring Cloud Data Flow, Spring Integration, and Spring Kafka. He is co-authored to Spring Integration in Action. Now I'd like to do a quick sound check for Joe. So Joe, if you would like to say hello to our audience, please let me know if you can hear Joe by posting a message in the chat panel.
Hello everyone, and thank you for joining us. Happy Wednesday to you all.
Great. Now I'd like to do a quick sound check for Marius. So Marius, if you would like to say hello to our audience, and audience, please let me know if you can hear him.
Sure. Hello everyone, and thanks for joining us today. I'm very excited to talk about all these things.
Great. And now I'm going to turn things over to Joe and Marius to begin our presentation.
Great. Thank you, Billy. All right, let's go ahead and get started. Yeah, we have a lot in store, so we'll just go ahead and share a bit about what areas we would like to cover with you today. So first, we're going to cover some of the challenges around deploying microservices, specifically with SQL-based applications. That's going to be part of our focus today, and breaking down what we're going to call the database monolith. And then we're going to go into some best practice use cases and approaches that we'd like to share on how you can better access and protect SQL databases in a microservices deployment architecture. And then finally, we'll land this with some more about NuoDB and how NuoDB can specifically help you deploy these types of data strategies inside of OpenShift that we're going to be talking about today. So as we get started, we're going to take a view from the CIO office. And well, I'm not a CIO, but fortunately I get to speak with many of them. And many of us here know NuoDB as well, and Red Hat also. So we have a pretty good view of what CIOs require these days and the challenges they're faced with. Many companies today are seeking sort of that next frontier of IT efficiencies. And typically it's around some of the same areas of saving OpEx and increasing bottom line. But today, to further it, the IT team must be agile, and they must respond more quickly to requests for change. Moving our applications to the cloud has really been one where there's this promise that the apps are, always on or always available, and with rolling upgrade and all of these capabilities. But that's a really hard thing to deliver on. And how do we actually, deliver on all those promises? So, if we look at, deploying and winning in today's cloud microservices and container deployment world, yesterday's tech no longer delivers. Monolithic software stacks with tightly integrated components means that everything must deploy together, like a bundle. And it sort of, slows the ability to push out changes quickly. And really data center architectures haven't changed much over the years with, the assumption there is that, migrations always mean downtime and scale up instead of scale out to increase performance. And high availability has really always been, the equation of high availability equals, high complexity and high costs. And really each one of these ends up being like a roadblock, when trying to deploy always on applications. So let's take a look at the effort to migrate an existing app to a microservice application. And again, we're focusing here on SQL-based applications. And really, as the first bullet sort of points out, most of the applications, these enterprise applications, are, if we generalize, many of them use SQL, right? They attach to a SQL database. So in moving to the cloud and trying to gain the kind of the scale out capability, switching to a NoSQL database could be one of those options, right? NoSQL offers, easy scale out. But when we look at the risks associated with, complete rewrite of the data management logic and retraining app developers and DBAs to learn new tools and migrating the data from a relational format to a key value store is a huge investment. So really, what if you could keep your SQL applications and still gain the same advantages of running in containers or microservice environment? So how to achieve this is really a large part of what we want to share with you today. So on this next slide, it goes into what we're going to cover a little more of what I was calling a monolith, the database architecture, right? I mean, traditional SQL databases, they were architected probably near about 3 decades ago. And the architecture was optimized for different infrastructure, right? Symmetric multiprocessing machines, scale up, not scale out. Memory was very expensive, and this is the kind of the world those databases started in. They require a lot of add-ons for replication and DR and backup and recovery. And of course, they typically have required expensive, dedicated, highly configured hardware to increase the performance. So if we look to the right, and this is where I show off my very fancy Google Sheet capabilities, I have built a stack of blocks. That stack of blocks indicates this monolith, right? And it's showing sort of these components that I mentioned that are sort of glued together tightly, right? And they sort of move as one. They're like Legos connected, and they move as one. But unlike Legos, they really don't break apart easily, versus a more containerized modular approach, which is where we're able to realize many more efficiencies, agile deployment methodologies and automations. And this is really the direction that we want to try to go. So, so if we take, here's a real example, right? A common traditional 2-decade-old Oracle RAC architecture, right? Difficult to set up, huge investment, complex. Again, these tightly coupled components of backup and HA and all this software that moves together. you know, with shared disk architectures and so on to sort of achieve scale out, but again, very expensive proposition, and still really only delivers high availability, not continuous availability. So with that as kind of a backdrop and an intro, I'm going to go ahead and turn it over to Marius, and Marius is going to take us through some of the data strategies for HA microservices and some of the best practices that, you know, Red Hat has to offer us as they work with their customers in the field.
Thanks a lot, Joe. This is a great introduction to the challenges that microservices developers and operators face, especially when working with relational databases. And as Joe has just mentioned, like at Red Hat, and especially with our OpenShift customers, with our OpenShift users, we've seen a lot of use cases. We've kind of gathered a lot of knowledge about the best practices that we have for running microservices, for running data services on a cloud platform. So I think it would be very useful right now to take a look and try to understand how things have come to be this way. Why are we using microservices? What are the use cases? And basically, what strategies can we employ to manage data in a microservice architecture? And then once we have that done, we can take a look at what the OpenShift platform has to offer for running both microservices and data services, and how to address concerns such as high availability and disaster recovery, right? And if you think about the motivations for microservices first, it's important to understand that, as Joe has mentioned earlier, for decades, the traditional development model was focused on monoliths. And monoliths were the norm, both in terms of both for applications and both for infrastructure. And that was a good thing because that brought a lot of cost efficiency. You were concerned how to minimize the cost of running applications, running infrastructure, running everything. And that's basically because when you're running everything on physical machines, or you're running everything on at best on virtual machines, the overhead of provisioning new resources, new machines, is very big. So there is an incentive to concentrate everything in one place, right? Cost was dominant, right? It was just more efficient, right? So from a development process perspective, this favors a very linear, almost like waterfall approach. The goal was to translate everything we know, like everything, like kind of develop a comprehensive view of the business domain, like everything there is there in a centralized data model. The database is basically is the center of the universe. You end up with these massive database schemas with like hundreds of, or maybe like thousands of tables, like encompassing everything in the in a single place. And then we started mapping POJOs and started creating monolithic applications that contain the business logic that talk to this database schemas. And that is a pretty fragile model, because on one hand, the monolithic data models around which the entire set of applications are structured are hard to change. So it's really hard to intervene and change something at the, like if you discover new things, if you want to adapt your business, it's actually kind of hard to do. On the other hand, the monolithic applications that are coming out of that are pretty hard to scale. So how can we do better? So if you go on the next slide, then we can take, we have different, like we are provided with alternatives. We can think in different terms about the relationship between data and applications. First and foremost, there are techniques like domain-driven design that are they're adding focus on better understanding the domain model from the perspective of features and subsystems and the way they interact with each other. So it's not only about modularization, it's also about thinking of all the interactions that happen in the domain first, and then starting to design different data models that fit the different subsystems that compose your application. Because really, like if you look at like even the same entities or even the same components, can be very different from a perspective, like from the perspective of one subsystem or another, right? A ticket or a flight can mean something when we're trying to book a flight, but it can be something very different when we try to check in to a flight, right? So we have an example over there. The net result of this is that we end up defining more granular, more focused part of the domain. We basically center everything around bounded contexts, which are, and this basically builds agility into the process, as we can start isolating change to individual subsystems without affecting everything else. And now that we put some modularization in place, we have options. So even before we talk about microservices, we can think about either deploying these parts together as kind of a more comprehensive applications, which is what we call in this case a fast monolith, or we can just deploy each of these bounded contexts as microservices, as independent deployment units. And the advantage for microservices is that they can allocate resources and scale independently. But in both cases, when you look at it, it becomes apparent that isolating functionality is just not enough. And in order for this isolation to be properly preserved, we also need to isolate the data models, and we need to isolate the way these components interact with databases. So we have to think about strategies that we have for handling data in this kind of scenario. So if you go on the next slide, then one of the most fundamental and typical strategy for handling for dealing with this is what's basically called one database per microservice. We can enforce isolation here, but just allocating kind of by using one database per microservice or per fast monolith. And it makes sense because as each bounded context has its own data model, they also have an isolated data store. And it also gives us a lot of flexibility in choosing our storage strategies. So you can have a relational database, you can have a NoSQL database, so you have basically choices. Now, one of the things to remember is that databases are, generally speaking, middleware. They are not designed, like at least traditional databases are not designed to be very lightweight components, right? So there are operational challenges with managing multiple traditional database instances. You cannot just launch and deploy like 100 of them if you have 100 microservices, right? So one of the typical ways to implement this is to maintain, to respond to this kind of limitation, is to maintain a single central database instance or a bunch of instances and use the multi-tenancy and isolation features, things like logical databases or schemas, whatever they call in their individual terminology, but then still maintain a logical database from each subsystem's perspective, right? And sometimes especially when you're having monolith to microservice migration scenarios, like for example what we can see in the following slide, you have situations where, like especially when you're extracting functionality and you're extracting microservices out of the monolith, you cannot really do this database refactoring. So you still have to maintain you still have to maintain a centralized schema. You still have to maintain a common data model. But especially when you have, for example, legacy applications that talk to that. But what you want is to be able to still construct these individual data models on top of a shared database schema. So one strategy here is, for example, virtualization, right? To deal with this impedance mismatch of having one single centralized database, one single centralized table model, but then have separate data models in each of these microservices or fast monoliths or components. Right. So it's important to remember that one of the goals is to recreate this effect of data model isolation that comes with one database per service, right? And how do we deal with one other consequence, right? Increased latency. So in the next slides, we need to talk a little bit about caching, right? One of the most common fallacies in distributed computing is that we can make remote calls behave exactly like local calls. And that's not true, right? I don't think anyone believes that. We have APIs that give us that illusion, but in the end, remote calls are remote calls. They go over the network, they have latencies, they have failures, all kinds of complications. And one of these is latency. So if you have multiple applications talking to each other, then calling other applications, which in turn go forth and call other applications, so you basically have this chain of invocations. Latency can compound really fast. So if you look at this diagram, right, the booking system kind of goes to check-in, goes to a bunch of other microservices, and so on and so forth. You can see, like, you can easily have five, 6, 10, like it could be a number of 10, like depending on how big these architectures end up. It can have like a chain of double-digit invocations as part of one call. So treating all of them as remote calls is just not feasible. You will end up having like massive latencies. So obviously caching can help here by reducing the number of remote calls, reducing the latency at each individual application level, right? But the problem that you have to solve in this case is to integrate these caches seamlessly with our databases. So just adding another, data store, just adding another system that your applications are talking to would actually increase the complexity of these apps. So this integration needs to happen seamlessly, needs to happen, almost transparently for the user. So that's another important thing that has to happen in these microservice architectures, and that's one concern. Now, this will give you a bit of an idea of what are the challenges, what are the strategies, and how we structure microservices, and how do they, like, what do we expect from the databases they're talking to. It's also good to take a look at how you run them and what OpenShift as a platform has to offer for running these applications. So if you go on to the next slide, you actually can see a picture, like a very succinct diagram of OpenShift as a platform, right? So as I said earlier, the high cost of provisioning resources as physical and virtual machines favors monolith due to cost reduction reasons. And one of the biggest revolutions in infrastructure management is the rise of the cloud platform. It allows you to manage resources dynamically and elastically, and helps you add modularization and agility into your process. So what we're going to talk about today, like one of the points today, is OpenShift, which is basically the leading Kubernetes platform that helps you build, run, and scale both applications and data services in the cloud, right? So that's a very, very, very important thing, because all that we talked so far, like microservices, data services, we want to run them on a single platform. And Joe will provide a little bit more about the motivations for that. But what I'm going to talk about next is a little bit, just give you a bit of a sense of how OpenShift works and how OpenShift helps into this process. So OpenShift runs containerized workloads that allows you to package your applications in an immutable structure and isolate it from the underlying runtime. Containers are deployed as pods on nodes, and the whole process is generally transparent and managed by OpenShift. From a user's perspective, the entire set of resources in a data center, or a portion of the data center, whatever you want to allocate for an OpenShift cluster, whether it's on-premise or in the cloud, is pulled together and available to be allocated dynamically and elastically, right? So that gives you a lot of ease in allocating resources, and that's basically what you expect when you run a large fleet of like tens or even larger numbers of microservices. You have to think about high availability in this context, right? So the fact that you can run multiple applications, for example, the fact that you can run multiple instances of an application, the fact that you can have like load balancing automatically between them, is basically something that the platform offers like out of the box. But you have to think about how you design these things. Like, for example, you have to think about the fact that applications that run 24/7, it is important that they're not disrupted. But applications crash, or they need to be updated, or the underlying infrastructure, like you basically need to upgrade, for example, OpenShift. You still don't want to stop running, even if you do that. So the common practice here is to run workloads at scale, using at least 2 pods, for instance, running on separate nodes. This happens like running pods on separate nodes is done automatically by OpenShift. And one important consequence of that is that the workloads themselves need to behave in a way that allows them to take advantage of this feature, right? So cloud native readiness is while OpenShift can definitely run applications that have not been designed to be cloud native, and that's actually kind of a big feature of it. That kind of readiness can help you improve your experience, right? And there are other features like which are listed on the next slide that helps you run scaled, highly available applications. So for example, we have liveness and readiness probes that can tell you whether a pod is a good or a bad state, whether it needs to be taken out of rotation for a load balancer, or it needs to be restarted because the application just crashed, so it cannot serve requests anymore. It allows you to tune resource usage. Again, a very important feature, especially when you're running resource-intensive workloads such as databases. It allows you to control pod placement. So while generally speaking, the optimal situation is when everything, like your view of the cluster is very homogeneous. Sometimes you want to target specific nodes with specific types of resources. So there are node selectors, which are an OpenShift feature, allow you to put certain applications to certain nodes if you want to. And very importantly, stateful sets. So that's basically like in the next slide, you have a brief view of what that means. Of course, a significant number of the workloads that run on OpenShift will be stateless. They don't have resources, they restart as a blank slate. So you can imagine an application that stores everything in the state in a database, or it stores some data in a data grid, or sends and receives messages. So those types of applications can basically restart, and they don't need to remember anything about what happened before they were restarted, right? This is perfectly fine. So that's a lot of the workloads are like that. But some workloads, such as databases or message brokers, and generally speaking, middleware, require some form of state retention. They need to retain some kind of sense of identity. So if I restart a database, for example, that's not very good if it has lost all the data that it had before. We just cannot have ephemeral database instances, right? So this is where like you need to have the ability for certain deployments to retain a sense of identity, like an ID in a cluster deployment, or a persistent file system, right, where they store all the information. And this is what stateful sets, which, as I said, are essentially a Kubernetes feature, and they're available in OpenShift, which is essentially an enterprise an enterprise platform based on Kubernetes. They are a very powerful concept that combines elastic resource management with the resilience of state retention. Each pod gets an identity, and that identity is basically matched with a mounted set of persistent volumes. So inside a stateful set, for example, when a pod is lost and needs to be restarted, a same pod with the same virtual identity is reinstated, and the associated storage is recreated, right? This is very important when you have, like, exactly for as I said, for databases and clustered. So in generally speaking, for clustered data stores, because obviously you don't want to lose your persistent storage, which is important. And the other thing is even if the persistent storage is reallocated to a new pod, you want it to retain its whole identity inside the cluster, so that all the replication processes and state replication features of the cluster can continue uninterrupted, right? So this is one other important building blocks in the notion of building data services and on top of OpenShift, right? And if we stop for a moment and kind of think about, like, this is all about how things happen inside one individual cluster, right? But we also need to think about how to enforce high availability at a larger scale and how to handle disaster recovery. So if you go on to the next slide, then you have like a few of the options for handling, like for managing high availability and disaster recovery. Now, the idea is that OpenShift by itself ensures resilience and reliability across a specific site. But you also want to be shielded from large-scale systemic failures, such as the entire site goes down or the entire data center goes down. So by its nature, OpenShift requires low latency networking between nodes. So basically means that each OpenShift clusters run on an individual site. You cannot run, for example, an OpenShift cluster across multiple sites, across multiple data centers. In this case, you have different strategies at your disposal. So first, you can essentially just run and maintain a single site, forgo disaster recovery, and whenever the site goes down, wait until it comes back again, right? It's a very simple strategy, but obviously probably not what you want if you want to run 24/7. You can fail over to a secondary site that remains inactive until required. So that's also a possible strategy. Basically, as we'll see a little bit later, this can come with some data loss, for example. And if you want to maintain a fully cloud native approach, you can run a multi-site application. So basically, this means that you have multiple clusters running across multiple sites. The clusters replicate data in real time. And this also has the advantage that not only all your clusters are active and ready to run, and they have, ideally they have the most up-to-date data with some eventual consistency limitations. But it also has the advantage that requests can be routed to the site that's most appropriate for the user. So for example, most geographically close to the user for solving latency problems, right? And the key here is that deploying multiple applications across the different data centers is not necessarily about the code. The key problem to solve is how you replicate your data. So you have a few strategies at hand. On next slide, for example, we talk about infrastructure-based asynchronous replication. So in this case, the task of replicating the storage data is undertaken by the application, by the infrastructure itself. This works especially well if the applications are read-only and only need to stay up to date. So one process updates one storage, and then everything else is replicated across the whole cluster. The other strategy that you have is application-based asynchronous replication, which is on the next slide. And essentially, this basically means that this is the most likely situation that you'll be in if you want to operate applications using relational databases. which receive continuous updates and need to propagate across sites. And when we say applications here, we just mean that this is not a storage infrastructure concern. How simple or how complex this process is largely depends on our database capabilities. Some databases can and will automate this process and handle it with a certain degree of transparency. In some other cases, you need to manually set up the replication infrastructure to propagate application data across different databases, or some databases can do this on their own, right? So this is I think one of the key points here, that the quality of experience depends on the ability of the database to handle this replication automatically, right? And just to make a brief point about the different disaster recovery approaches, we have essentially two. So on the next slide, for example, we have basically a couple of variants of standby. In both scenarios, you have an active data center and you have an idle and offline data center that's kind of ready to take over if the application, if the primary data center goes down. Now, this comes with this increases the likeliness of data loss because the backups are periodic. So all the data between two backup instances, two backup events, is basically lost. On the next slide, you have a slight improvement, which is maintaining a hot standby, maintaining a standby data center that is only used for, as a backup or at best for read-only operations. And this minimizes the chance of data loss. There is still a lag between updates, but that is minimized by the continuous replication that takes place between the active and the standby data center. And of course, on the last slide is basically the active approach, which essentially means that all the different replicas are active, all the different replicas receive data from their applications, and the integration and replication happens in real time, right? So obviously, this is the kind of the most the one that offers you kind of the most resilience in a way, but it's also the most complex of the three, right? And with that, I'm going to hand it back to Joe to talk about how NuoDB handles these strategies.
Great, thank you, Marius. That was terrific. Yeah, I would. You've shared a bunch of useful information about OpenShift and deploying in microservice environments. Yeah, I would just like to take probably the next 10 minutes. I'm going to talk a little bit about how NuoDB helps deploy these strategies that Marius was referring to, and then we'll also open up for some Q&A. So I'm going to start with first describing some of the pitfalls that we might see, and we've kind of been touching upon it a little bit, but when we want to deploy applications in microservices, and in this example, OpenShift, we of course want to do that to go ahead and gain those agility and automation benefits by doing so. But when that application is a SQL-based app, and you kind of get this, right? If your database doesn't really run well in containers, based on a lot of what we've been talking about today, the natural first thing to do is sort of run it outside, right? You poke a hole through the OpenShift containerized network to an external network, and you're able to run the application in that way, but you really haven't achieved all of the agility and automations that you were hoping for. You create network overlays that are complex, and it introduces security concerns, and it's sort of like crossing a bridge halfway, right? Your application is running in the environment you want, but now you're stuck managing two separate environments because your database is still running the same old way. Now we can make a slight improvement, right? We could run a data cache inside our containerized environment, and many of you may be familiar with these third-party client memory caching tools. to improve performance, but they're not a panacea as well either, right? Because it still requires application development and management to ensure that you maintain consistency between your caching layer and your database. And then there's this sort of third one that I've kind of pictured in this, swollen container-looking environment here, where, well, what if we took the entire monolithic database and we ran it in a container? Well, that doesn't fit the model either, of course, right? Containers were not designed to run, complex multitasking database systems. So again, you don't get the benefits of the microservice deployment environment, and the ability to leverage these automations that we've been discussing. So we're really looking for a different approach, and I would describe each one of these as sort of that square peg in a round hole. But when we look for that better approach, we want to look for something where we can deploy a single operational environment, right? One environment, not the two, and then by doing so, we're going to lower operational costs. Right now, we're maintaining one environment, which is of course the goal and the ideal. And by maintaining the one environment, and this speaks to some of what Marius was describing earlier, but the benefits of running a localized database now in an OpenShift container network, you're not going to incur those latencies of those remote database calls, right? Your database is effectively running inside of OpenShift as an embedded database. And then, deploying NuoDB as a container native database, because NuoDB is leverages a redundant process architecture, it allows the database to scale the transactional layer and the storage layers independently. And we'll see what some of those benefits can be realized coming up. And then lastly, the increasing developer productivity through the same sort of CI/CD continuous integration and continuous deployment pipelines that you want to use in your microservice deployment environment. So NuoDB is deployment agnostic. So if we look at the scale-up nature of the non-container databases, they must deploy on specific systems that were configured in a special way to get the performance that you need. And because of that, they are generally deploying outside of the container network, as I was showing on the previous slide. NuoDB's processes run wherever you like. They can run in containers, VMs, virtual systems, physical systems. So they really are deployment agnostic. They are processes that are going to run within a process space. And this allows for much greater agility and deployment automation. So here's a picture of what that would sort of look like. So NuoDB is a container native SQL database. It's inherently a distributed SQL database. It offers the scale out by simply adding more nodes, means adding more database processes to handle more transactional throughput or more storage durability. To the right, we see the TEs. Those are the transaction engines. That's what's servicing the application transactions. And the SMs are the storage managers. That's what's persisting the database to disk, using a lot of the technologies that Marius was referring to, node selectors and stateful sets, and leveraging PVCs, persistent volume claims, to ensure that the data always resides, that it's not ephemeral. So the last point here too is this idea around the built-in data protection. The SMs automatically sync with each other. So it's offering now continuous availability. There really is no failover event on DR. If you should lose a process, either a TE or an SM, the database continues to run. As long as there is a single TE and SM, the database will run. It may see less performance, of course, because you have less processes servicing applications, but it's all about continuous availability. So just wanted to also touch upon the in-memory cache. These TEs that I'm mentioning, the transaction engines, they are effectively a distributed in-memory cache. Each one of them is keeping a cache of the database, so the database continues to run at optimal speeds. If the data is not available in a current TE's cache, it can grab another data element, or as we call them, atoms, from another local TE, its nearest neighbor, if you will. And this effectively creates this distributed cache and offers very low latency transactional data access. And speaking more to the kind of the HR and how the system protects itself, Marius was talking a lot at the end about active-active and how that can be difficult to to deploy. But with NuoDB, it's native to the product. It is an active-active, always-on architecture. So here, where we see like a zone 1 and zone 2, these could be availability zones. As we spread the NuoDB processes, these engine processes, onto the availability zones, we have 2 in each zone for the transaction engines. Each one of them are running in a pod, those pods that Marius was describing earlier, as well as the storage managers are also running in their own containers or pods. So if we should lose 1 or 2 or even a complete zone, our database remains available. And perhaps that could be what was so important to the top requirement the CIO had earlier when we were referencing it, is this idea around the application must always be on, must always be available. And NuoDB can achieve that in an OpenShift orchestrated process environment. This is just a quick example of what I mentioned earlier about if the database can scale independently, the transactional and storage component, well, now your database can serve many different applications uniquely and specifically to the requirements, right? For web mobile apps, we can scale more TEs than SMs. For OLTP, we may want to run about the same scale, right? Logging apps, we need more storage, right? We're going to scale that out so we can log faster. And for an HTAP, a hybrid transactional analytical, we may actually configure those TEs differently, some with more memory, some with less. So you now have all that great control available to you. I talked a little earlier about the the deployment model of continuous integration and deployment, right? You want those same benefits for your database. We talked about crossing the bridge halfway. Well, we really don't want to do that. We want to cross the full bridge and take full advantage of the OpenShift microservices deployment environment by also adding the database to your pipelines and allowing for rolling upgrade and implementation of operators for many of your operational type tasks can be easily now automated. Okay, and that brings us to the idea around automated operators. Again, another one of the Kubernetes features, and this is a feature that we're currently implementing now, Kubernetes operators, to simplify all of these areas of rolling upgrades, scale in and out, backup and restore. And I thought I would just finish with a quick little view of just what does a NuoDB database look like inside of OpenShift. I took a little picture here. So you could see up above is the NuoDB monitoring interface that's showing that we have 2 running transaction engines. I'll point them out here. We have 2 storage managers. We can see the memory and CPU footprint for all of the running pods on the system. And we happen to see here in the middle the aggregate transaction throughput, where I was scaling up the number of transaction engines, which doubled the throughput of the application from about 50 to right around 100 transactions per second, simply by clicking up on the number of OpenShift transactional pods. And with that, I'm going to go ahead and land on the thank you slide, and you have some links here on how you can learn more about Red Hat and NuoDB and what we're doing in the microservices deployment architectures for your applications. And yeah, I wanted to turn it over to Billy. And Billy, do we have those polling questions that we would be able to share with our community? Here
Here
are
you go.
polling.
Here's the first poll question.
Great. Thank you, Billy. So we have a few polling questions we thought we'd have a little fun with, just to, are you considering deploying a microservices architecture? Please submit your answers and we'll get to share all our results for all of you.
Close the poll in about 10 seconds.
Then we just have two other questions and that build upon each other to give you all hopefully a sense of where maybe you're at in your own microservices deployments and what you may be considering over the next 6 months or so. Billy, do they get to see all the questions? Oh, okay.
It's just one at a time. Here's the results for the first one.
Awesome, thank you. Well, overwhelming, looks like many of us now are considering and on our way to deploying microservice architectures. Billy, why don't we try for the next one?
All right. Here we go.
Are you considering deploying the OpenShift platform in the next 6 months? I don't know if many of you were out at the Red Hat Summit, but I know I met many of you there and others, and many were there to learn more about how to deploy OpenShift and enhance their current deployments.
I'm going to go ahead and close the poll and show you all the results.
All right. Would be good also there to see the next 12 months as well. Let's go for the next.
All right.
Looks like we've got about 30. Great. Thank you, Billy. So it looks like we got about 30% of you that are already looking to deploy OpenShift in the next 6 months. How about of those, and this is where we touched upon a lot of these enterprise applications are SQL-based. How many are looking to deploy SQL-based applications in OpenShift in the next 6 months or so? And hopefully, as you're considering deploying that, you've learned some new techniques today on how you can actually run an embedded SQL database right inside of OpenShift to gain all the agility and automation and performance benefits that NuoDB can provide.
About 10 more seconds and I'll close out the poll.
All right, sounds good, Billy.
All right, here are the results.
All right, so just about 25%, 1 out of 4 are going down this path right now in the next 6 months of deploying SQL-based in OpenShift. So that's fantastic.
So,
and I do imagine over the next 12 months, of course, those numbers need to increase. But that's very useful. Thank you, Billy.
Of course. I'll hide the results now. And would you like to do the Q&A portion now?
Yeah, that would be terrific.
Awesome. So we had a few questions come in from you guys. The first one is, how can I start using NuoDB on OpenShift?
Well, one of the easiest ways to start is we have a container that's available along with a YAML that will allow you to deploy the environment. In fact, you're seeing right now an OpenShift environment, and that's what I've done is I basically did add project and it started a database right inside OpenShift. We are currently updating our container right now to add stateful sets, the persistent volume claims, as well as the YAML file deployment. So within the next week or so, look for our container up on the in the OpenShift catalog. And of course, you're always welcome to contact us through our website or through the contact information we provided in today's presentation. But it's very easy to get up and going and running with NuoDB inside of OpenShift.
Great. The next question is, do you have an optimal way to implement event sourcing?
An optimal way to implement, sorry, I missed that.
Implement event sourcing.
Event sourcing. Yeah, so I think the question is around when the database has events and alerts, how we can then propagate those. So we do have our own set of events we're sourcing, and those will go into the environment that you see on the upper part of your screen, the monitoring place. We're currently building this out where we're showing the more OS-related metrics and transactional pieces, but we're also going to source events and show alerts of what may be happening in the environment, and then how to root cause those types of database issues. And go ahead.
I would like to add, like, a compliment to what Joe has just said. So for event sourcing on, especially for event sourcing applications on OpenShift, we have support through. So there is a project that I strongly recommend you to take a look at, which is called Debezium. That is used for implementing CDC on top of a number of relational databases. I don't think, I'm not sure about any plans right now for integrating with NuoDB, but essentially what it does is it monitors all your transactions and all your changes to the transactional log, and it sends them to Kafka as standardized events. So that's one of the things to look at in the OpenShift Red Hat universe. So that's kind of a good complement. Again, I don't think it applies necessarily to NuoDB right now, but I think, Joe, what do you think? I think that could be an interesting addition for the future.
Absolutely. Thank you, Marius. That's really good information.
Awesome. Our next question is, any tool migration from RDBMS to NuoDB?
So RDBMS is a traditional relational database. NuoDB works with traditional databases from a data migration standpoint. It will easily migrate the data from that database into NuoDB using our native migration tool. So we try to make that very simple. NuoDB is it's an ACID compliant and full ANSI standard SQL database. So all those SQLs that run against RDB is going to run against NuoDB, and that's really what we talked about in the earlier part, is that the NoSQL is a tough transition, but when you transition from an already existing SQL database to NuoDB, it's quite simple.
Great. Our next question is, can I copy SQL Server databases into NuoDB?
Yep, that's very similar to the previous question. Again, we work with all of the main database products. We will read and extract data from a SQL Server. One of the important pieces, what NuoDB does, is it's looking at the source data types and then how to then translate them into the receiving NuoDB data type. So the data movement and streaming is probably the easy part. What NuoDB does for you is it makes sure that your data is coming over into NuoDB as the proper, string or char or date or numeric type, integer or decimal, so that your applications continue to work as expected. We also have a migration webinar on our website. If you care to look more and learn more about that, just go up to nuodb.com and look for the data migration webinar. We actually migrated a MySQL database during the webinar in 3 easy steps. So it's kind of fun. Please go out and enjoy that as well.
Thank you all for the questions. And I'd also like to thank Joe and Marius for a great presentation. And I'd also like to thank today's sponsor, NuoDB, for providing the DZone audience with a great webinar presentation. And I'd also like to thank everyone who joined today. We hope you learned something new today that'll help you in your developer career. Have a great day, and we'll see you next time.
Thank you very much. Have a great day.
Thank you.